Okay. So we're actually going to jump into chapter 10. Yeah, chapter 10. And part of the rationale behind this is if I'm going to teach you the alphabet for the first semester, which is primarily derivatives, I'm going to teach you all the alphabet. We're not just going to teach some and then go through the course, and then in chapter 10 at the end of the year, teach you the rest of the alphabet. So what we're going to attack today and some tomorrow is parametric equations and polar equations, and how I would find derivatives of those two. Okay, yes? Sweet. All right, so now this isn't all of chapter 10. I think it's like 2:1, maybe, I'm sorry, 10:1, maybe through 10:3. Okay, my hope is that you were introduced to these in pre-calc. Does anybody remember what a parametric equation would even look like?
It's like y equals something plus t and x equals something plus t.
Okay, so basically you're going to have an x equals equation and a y equals equation. However, we're going to have this third variable, and in most problems we call it t. T is what we call a parameter. I don't know if you've heard that before. T is time, and in most real-life problems that's the way it works. Okay, so we're going to have this function x equals f of t and y equals g of t, where t is time and we call it a parameter. Now, what's cool about these types of functions is we can do, in fact, I did this, yes, my last multivariable class. You don't have to have t as your parameter. You could have another function as your parameter. It's called parameterization. And that's, we're not quite there yet, but please don't go to guidance and get out of my class. Okay. But for right now, we're going to use t. And so what's cool about parametric equations is I'm going to be able to say if I graphed this, if I threw this pen like across the room, now that I have a third variable, I'm going to be able to track this pen's height, its distance traveled, and the time component. So all of a sudden, instead of like just doing an x and a y coordinate plane graph, I can actually track 3 things. I don't know if that makes any sense. Do you remember this vaguely last year or the year before? Okay. All right, and so let's just start off with an example. Okay, now, I have yet to discover negative time. That would be so awesome. But let's just assume for this problem, because remember, it doesn't have to be time, it can be anything, but let's just say that I would like to graph this parametric equation from -2 to 3, and those are t values. So I have x equals t squared plus 2t, and I have y equals t minus 3. How would I go about doing this? And there's actually really kind of 2 ways. Poe. Yeah, okay, and so Bobo the monkey boy. Now, if I set up a table of values, how many variables am I going to have? 3, right? And so I could literally just start at -2 and go to 3, and then what would I have to do with these values? Plug them into both equations, correct? And I would get values. Now, I'm going to assume that you can plug in as well as I can. So can I just list them so that we don't have to sit here and waste time? Okay. All right. So I got something like this. If you find a mistake somewhere, please let me know, but I believe these are all good to go. Okay. And just in case you're not certain where I'm getting these values from, I take -2, I plug it into t, and for the x equation, I crunch the numbers, I get 0, and then I'd plug -2 into the t for the y, and I get -5, and I would just do this over and over and over again. Josh?
So that range is for t, not for x or y.
This interval are for t values, correct? Yes. Yeah, so now if I started asking you what the range and domain of my function was, I'd be looking for x and y values. But this interval is for my time. Okay? Yeah, that's a good question. All right, any other questions so far? I don't think this is too bad. Okay, so what I'm going to do is I'm going to erase all this because I have to use the center board. And I would like you to try to graph this function, please. Now, I would like you to try to graph it on an xy coordinate plane. Now, does anybody remember how I'm going to denote my t, my parameter? Does anybody remember this at all?
Is this the one with the arrows?
Yes, this is the one. These are the type of problems where I'm actually going to put an arrow on my curve. Okay, and do you remember what that arrow helps us do? Yeah, that's our orientation. So that basically is going to tell us which kind of way, as time goes on, which way I'm going, because without that, I won't know unless I look at the table of values. Okay, so why don't you try to graph this with me, and then we'll examine it for a minute or two. Now, obviously, Mr. Baird, wait a second. We've been doing a lot of derivatives for the past few weeks. What does this have to do with it? Well, this is kind of all review. We're about to take a derivative of a parametric equation, and it's different. But I figured I'd show you how to do all this, just in case you were maybe absent or not. Man, that's a slanted x-axis. No. I'm going to extend this thing out fairly far, because I believe my x values got big, didn't they?
Yeah, 15.
Eins, zwei, drei, vier, fünf. Okay. 1, 2, let's see here. 1, 3, -2. Is that right?
Yeah.
Getting old. 8, -1.
Oh,
I'm just plotting points. I'm sorry.
Yeah.
Yes?
yeah.
15, 0. Okay. So what I get is this. Yeah? Okay. Now, these arrows. Where would I put my arrows? Do I need to put them at every time interval? I don't need them at every time interval. But here's the question is, would my object be doing this, or would it be doing this? Because, I mean, it's a legit question. Yeah, I believe it's doing something like this, isn't it? Okay, and we call that the orientation of my curve. Now, what will end up happening for a lot of problems is what I recommend, is I recommend you actually, like, you can put the time on your graph. Do you always have to do it? I mean, it just depends on how sneaky you want to be. But basically, now all of a sudden, I know exactly what this object's doing. I know what it's doing. I know its x, its y components. I know exactly at what time it's doing, and I know, like, my orientation. So that's a pretty good graph. Tells me a lot of things about my object. Questions on that? Okay. Does anybody know what this is graphically? Say again? Oh, I'm sorry. I meant like shape. Yeah, I mean, I don't know. Once again, first of all, I don't have negative time, and yeah. Aiden, it's a sideways parabola. Could you write the equation of that sideways parabola? Maybe. If my life was endangered, possibly. All right, well, it just so happens that we have something called eliminating the parameter. Okay, now, you obviously have the two equations, right? Okay. What do you think I mean by eliminating the parameter? Kill it. Good. Yeah. T in this problem was the parameter. I want to get rid of it. And then what am I going to do? How am I going to get rid of it? Yeah, so basically, I told you this is true. And I told you this is true. So, which one do you think I could probably isolate T best in? Yeah, okay, great. So I'm going to add 3 to both sides. All right, and then just like in Algebra 1, teacher should have taught you, I can take this expression for T and do what? Plug it in everywhere I see T into the X equation. Great. All right, so when I do that, is everybody tracking what I'm doing? This isn't too bad. Okay, I get this. Okay, I get x equals quantity y plus 3 squared plus 2 quantity y plus 3. I'm just going to do the math on this just to show you. Okay, now. How much algebra review we want to do? All of it. What the? Can't do all of it. Oh, we're going to do some good stuff here with this in a second. Okay, so I have x equals y squared plus 8y plus 15. Who agrees that that's a sideways facing parabola? Remember, it's not y equals x squared, it's x equals y squared, so that would make sense. All right, now, let's do some cool stuff with this thing. The first cool thing I could do, if I rewrote this, I could factor this. And guess what these are? Not the zeros, they're my y-intercepts. That sounds weird, but remember, this isn't a function. But yeah, look, -5 and -3. Booyah. All right, now that was kind of JV algebra, but yeah, everybody see that? Okay, well, let's spice some things up a little bit. When I taught Algebra 2, I called this the Barredian method, but I don't know how they show this to you. What if we did this? Can somebody complete the square here? Forget about the 15. I'm sorry, ladies and gentlemen. Yeah, I don't want to erase. Can you see that? Okay, watch this. You ready? I'm going to add 16. Now, you all probably been taught the golden rule of algebra, which is whatever you do to one side, do to this other, right? But why can't I do this? Well, but look what I basically added 16 and I subtracted 16 to the same side, so what have I done? Absolutely nothing. However, watch what... Yes, Mr. Baird, you've done absolutely nothing but bring pain to my life. All right, but watch this. Look what I've really done. I can complete the square there. And then that's -1. That's vertex form. That's vertex form of a parabola. Now, you're used to seeing it like this. Because you're used to playing with parabolas that open up and down, right? But this guy goes side to side, so what's my vertex? You can look at the graph and peek and cheat. It's -1, -4. So look, the H and the K flip. Ooh, spicy. Yeah, nice. No spicy? Okay, now, Mr. Baird, why did you put me through all this pain in algebra review? I like algebra. I like algebra. I don't remember how to exponentiate, but I like algebra. Okay. Why would this be beneficial? Why would eliminating the parameter be good? What would it get rid of in the beginning of my process if I asked somebody to graph this thing? The table would be obsolete. The table would be obsolete. I gave you all those numbers, but Bobo the monkey boy would have to compute all those numbers and waste time. Mr. Red, that was a lot of. But yeah, but factoring's I mean, that's easy. That's not hard.
So it's kind of like when you do like f of x equals a function, so you plug in a number for x to get your y, so you're basically doing the reverse of that. To find your numbers.
Well, what I'm saying is, I don't know if I had to say exactly that, but what I'm saying is instead of doing a t, x, and y table and getting all these points, okay? If I know that I'm dealing with a parabola whose vertex is at -1, -4, I can just plot this point and graph my parabola that goes sideways. Okay, there's one caveat though. What do you think I have to keep in mind if I do it this way, which is probably quicker for a lot of us? I probably have to plug in these 2 points into my equation, don't I? Or my equations, because I need to know where I start and stop. The rest of it I could probably figure out the orientation. I don't know if that makes any sense. Because basically what I would have is I would have like this sideways parabola graphed, but then I'd have to know where I start and stop, and so I would just erase. I don't know if that makes, no, maybe. Okay, do you think I care which way you do it? No, I care if you do it correctly. Yeah, okay. All right, are there any questions on basic review of parametric equations? All right, well, let's get to my class then, which is the derivative of these. Wait, Mr. Red, that's the hard part. Okay, I'm going to take you back a few steps. I'm going to keep the graph up here just for viewing pleasure, but let's go back up to this right here. Okay, that's the equation of that, isn't it? Okay, can you please find its derivative? Find dy over dx, please, since this is my class. Dy over dx, so I'm finding the rate at which y changes with respect to x. So I want dy over dx. Alrighty then. I'm going to be not happy if this thing conks out after like 25 minutes. Son of a biscuit. I don't know, it'll probably blow up. Just tap it?
Yeah, just use your clicker.
Well, I mean, it's going. I see the 1920. Oh, I've already been talking for 20 minutes. Jeez. Man, time flies. I need more time. Any joy? What type of differentiation am I doing? Implicit, great. I get 1 equals 2y dy over dx plus 8 dy over dx. Most of you did a pretty solid job on this on your quiz. I can factor out the dy over dx and then divide, and so I get I'm hoping you can kind of visualize this. I'm going to flip-flop my sides, but I get this. Yeah? Okay. Questions on that mathematics? I think that's pretty straightforward. And guess what? If you have a y value, I don't know, pick a y value. 2. 2. If I put 2 in here, let's see, 2. Oh wait, 2. I don't have 2 graph, but I could pick 2. Negative 2. If I put negative 2 in here, I get what? 3? Whoa, 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 whoa. I'm talking about into the derivative. What I'm saying is, if I evaluate this, I get a 4th. Yes? Okay, well, look at my graph. I mean, that looks about right, doesn't it? Yeah? What if my y value is negative 4? We'd be in trouble. Vertical tangent line. Undefined. Not differentiable. Do you see? Okay. Interesting. Amazing. But Mr. Bear, that's a whole heck of a lot of work. Is there a faster way? Yes, there is. Does anybody think they know the faster way? Low, be tall, he says. What the? There's not a limit in this problem. You could make one. Yeah, you could. All derivatives are based on limits. All right. Please get this copy down. As spicy as this is not nearly as good as the polar coming up after lunch. What was that? Mr. Barrett, I don't even know what a polar is. Parametrics. Okay, dy over dx. There's a formula. And I don't think it's going to be too hard. But remember, you're going to be given x equals and y equals, correct? So I'm going to judge, but that should make sense logic. I see James going like, yeah, as few of you are not. Yeah, I mean, that does make sense. So I have 2 rates that are going to give me this 3rd rate that I'm looking for.
In English, is that just the derivative of t with respect to, or with respect to y over, or wait, y with respect to t?
Yes. The rate of change of y with respect to t, the rate of change of x with respect to t, that ratio will give me the rate at which y changes with respect to x.
Okay.
Yep. Yeah, that's good. No, this is, you want to know what it means. But does that make sense? I think if you think about it, it would make sense. Okay, I'm about to give you the second derivative because this does come into play. Now, I haven't even really breached too much what the second derivative does. I'll do more of it in chapter 4, which is coming up real quickly, but for applications. So this is the first derivative. The second derivative is, I mean, we've played with the second derivative a little bit, but now this is very nasty. A lot of people mess this up. And for parametrics and polars, these kind of look very similar, but they're different than maybe what you would think. I don't have a ton of time. The book actually does a pretty good job explaining why these formulas work. So let's think about this for a second. Most people get messed up right here because this is the same as the beginning. But look at what this is saying. I'm going to take the derivative, but then I'm going to take the derivative of the derivative with respect to t, and then I'm just going to take the derivative of this part of that derivative. It's nasty. I'll do a problem with you, and I'll hopefully make it make some sense, but a little nasty. And that's not a typo. Hi.
So the top one, the dy over d goes into that.
This answer would go right here, and then you would take the derivative of it with respect to t and divide through by dx over dt. That's what it's saying. But you'll already have you'll have most of this already done, won't you? You'll have that, you'll have that. You'll just have to take the derivative of the top with respect to t. Obviously, we're dealing with 3 variables, aren't we? So there's there's a lot of moving pieces for a parametric equation. Okay, can I show you a problem and then you'll kind of see, oh wait, that's not too bad. All right, well, why don't we do this? We're going to go back to Old Faithful here. I've asked you this a bunch of times. Now this will not be a typo either. Okay, will you please write the equation of the tangent line to the parametric curve x equals t squared plus 2t, y equals t minus 3 at t equals 2. Now I'll give you a hint. We've been playing with this thing for the past 25 minutes. Okay? However, so graphically speaking, you know what it looks like. But think about the mathematics that I just put on the board. Do you want to give it a shot? Do you want to try it? Okay, I mean, you're just plugging and chugging for the most part, but you got to keep track of the formulas. And keep track of your notation. Now, what do I need to find the equation of a line? I need a point and I need a slope. I don't have either. Good luck. But you can find them. I got a point, Aiden. And I would like you to use the formulas. Is there another way to do this? Of course there is, because we just found the derivative. Like I want you to use the formula that I just showed you. Like I don't want to use the formula that I just did 5 minutes ago, where I got it x equals and took the derivative. I want the dy over dx, so I want dy over dt. I just want you to do it that way. Say again? It better not give you a different answer. Yeah. Do it. I promise you don't get a different answer. If you get a different answer, Mr. Bear needs to go back to teaching history. I'm certified 6th through 12th grade history. Yeah. I did. I never taught history here. I taught at T.C. Williams, World History 2. Oh, you sound like my Adelaide for the longest time. And I just said, listen, you just have to get one good teacher who engages you in it. Because it's interesting how it works. And it's much more competitive banter than this class. I mean, I love teaching math, but history you can debate.
I like government better than I like.
Government's not bad. Yeah, government's not bad. Yeah, but history's fascinating. Some of history's fascinating. Some, right. Others is dry, but that's depends what you're studying and who you're. Whereas this is just all awesomeness, 100% of the
That
time.
is actually exactly what I was thinking.
Yeah, I'm a mind reader. What can I say? Anybody stuck on anything or just not understanding what I'm asking, or do I care whether you get the point or the slope first? No. I typically get the point first because sometimes sometimes what'll happen on a crazy problem is you'll go right to the derivative and it'll take you forever and you forget to get the point. And then you're kind of like, now what do I do? You'll see what I'm saying. I mean, I don't do that, but you guys will. No. On the x point slope form, my x's and y's are the same. I just flipped them the other day because we were doing inverse functions. Aiden, did you still disagree with me?
I thought about sprinting to white. Like, I didn't think that would work out.
Yeah, okay, that's fine, but it's dy over dt over dx over dt.
No, this would just be dirt.
So it's going to be 1 over that.
Once I tried to with my other
Yeah. Whoa, yeah, you're right. It shouldn't be most of the time, but think about it. What variables are we playing with? We're playing with different variables. Your derivative is going to have t. This should have t's in it. That didn't have any t's in it. That was all x's and y's. Yeah, I saw the light bulb click. You agree with me? We're getting the same answer, dude, because this stuff is gold. It's gold, baby.
I have a notation.
Yeah.
So when you're finding the slope,
Yes. That's wonderful notation. All right, how many of you are getting some logs? Are we moving? Okay, because I'd like to finish this one up and let you try one more on your own just so that it's in your DNA. All right, so you agree? All right, so how would I get a point? Yeah, I'm just going to plug in 2 in for t. So I get x of 2 is 2 squared plus 2 times 2. What's that? 8. And then y is -1. Okay, so I believe I'm looking at the point 8, -1. Okay, so now I have the point. So I'm 50% of the way there, even though the mathematics is still a little much. All right, so questions on how I got the point? I think that's pretty easy. All right, so what do I do with my formula? How am I going to get dy over dx? So I get dy over dx, which is dy over dt over dx over dt. Did anybody take the derivative of the y with respect to t? 1. Okay, cool. And then 2t plus 2. Awesome. Okay, now, Aiden brought up a great question. He said, but Mr. Baird, if you look at the beginning of my problem set when I introduced this, we found the derivative, but they're not the same. And they're not. But they're not gonna be most of the time. Because, notice, this derivative has t's in it, whereas the other derivative did not. It had y in it. So, yeah, but you're gonna get the same answer, promise. All right, Ms. Harriman, and so what do I do next?
You do dy over dx at t equals 2. And then plug in 2.
Do you see why the notation's so important? The notation tells a story. So I get, what, 1/6?
Yes.
Okay, now, go back to the previous one. Let's finish the problem first. So now we have everything we need, right? So the point slope form is what?
Y
Plus 1, yep.
equals 1/6 of
Okay, cool. So if you would graph that parabola up above the x-axis, this would be its tangent line at t equals 2. Yeah? Not bad? Not too bad. All right. Just real quickly, who had the other derivative? from the front or wherever your notes are.
1 over 2y
Plus 8. And what is the y value at t equals 2? But notice the notation. You would be using this. And guess what you get? Yeah, you do. Okay. All right. Do you want to try one more? Yeah, I'm sorry. Point slope form, PSF. It's something, unfortunately, a lot of Algebra 1 teachers don't teach you. They always go slope intercept form. But see, the problem with slope intercept is I got to do a lot more math to get the intercept, the y-intercept. Point slope, baby. Point slope, go. Next problem.
Will those two always be the same?
They always give you the same answer. They're not going to be the same function.
So if we find that and it says find the slope at this point, we could use it.
Just, the thing I need to caution you with is the notation's uber important. One, you're plugging t into it. The other, you're plugging y into it. But you get one, it's always going to work. All right, let's try one more, and then when we get back, we'll do polars. Actually, stop that for a second. Find me the second derivative, please. Mwahaha. Mwaha. Ha 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 ha. My evil Scooby-Doo laugh kind of ran out of steam. All right, yeah, let's find this while we're here. I mean, what else are we gonna do? Cry. Good. At least we found the first derivative. Now you can cry. Yeah, that's fine. Is it bad if I just tell the kids tomorrow just to put headsets on and watch? Okay.
You should write a note on Blackboard though to bring headsets.
That what?
To bring headsets, like today, put that on Blackboard.
Don't you all have headsets? You all have
I mean, I
headsets.
don't bring headsets.
No? To listen to music? I have to check your pulse, make sure you're breathing, and I'll call CP, do CPR. You don't either?
They're Bluetooth and they die within 20 seconds.
Well, yeah, well, right, well, because they kind of made a... Irving is device-free, which is great. They go to their locker, and they put it in their locker, and the bell rings. I think it's great. No, my daughter... Well, okay, that's what they say, but... True. I don't know if it's in principle. Or principle's right, but... It's a woman now. She's pretty decent. I think she's decent. Yeah, that's it. Comic.
I heard that they made them sit in a science scene something.
Not sure about that.
A science scene?
Yeah, that's what my little sister said.
Do I have to do a lot of work here? I shouldn't have to do too much. Should I? I don't think so. Don't I already have dy over dx? Yeah. Okay, now, you could do the quotient rule, but couldn't you rewrite? Yeah, how could you rewrite dy over dx? I wrote it as 2t plus 2 to the negative 1. And then what was dx over dt? 2t plus 2, wasn't it? Alright, and so if I do this, I just take the derivative of that, which is the chain rule, and I get negative 1, or just negative, 2t plus 2 to the negative second times the derivative of the inside. Give me 1 second, I'm so sorry. And so I get this as my second derivative. If you were to kind of tidy that up a little bit. Because I can bring this down, and now I'd have 3 of them. But notice my second derivative is still in terms of t, isn't it? Okay, questions on any of the math I've shown you so far? Okay, I hope you guys have a great lunch. I will see you when you get back.